Okay. Okay, so we'll go over the assignment, and guys, please do me a favor, stop me at any time. Like when you're checking your answers, if you don't have the same answer and if you can't find where the glitch is, just ask me. We might be able to resolve it. And so don't be afraid or don't be shy. There's absolutely no reason to be shy or afraid to ask questions, to stop me and clarify whatever the hiccups are. I call them hiccups or bumps in the roads. And let's just make sure that we're all learning how to do this properly, and that's my objective. So if ever one day you need to do this for whatever reason, you'll be able to do it with a certain level of confidence, and that's what's important. Okay, so here we go. We will am I I'm not I haven't sorry, I have to stop this. I forgot to press. Yeah, we are recording, right? Okay, sorry. Go back to okay, so basically assignment number 3, I like to annotate, so I might as well put that there and go here. Okay, so this was our little problem, okay? And here what I did, I kind of like made it simple for you. I kept it to 6 meters, so therefore only this, like the exposure factor here would be here. Of course, the plan view, it allows you to use that, like I said, like as long as the plan view is greater than the height of the building, you're allowed using those values that you have in that table, and so on and so on, okay? And calculate the external wind pressures acting on the building shown below according to, and Livy, for those of you that might have a trouble finding it, well, Livy is a little borough outside of Quebec City. So if you looked in the Quebec City area, you would have found the climatic information for Livy. Now, the importance factor is post-disaster. I do this so that you guys can get into the habit of realizing that, like there are different importance factors, and post-disaster is 1.25. High is 1.15 and normal, and then of course don't even bother with low. Okay, so what we tend to do is, okay, what we tend to do is, of course, this is the equation that we use to calculate the wind pressures, and therefore the first thing I worry about is what is the importance factor. In this case is 1.25. Where do I get the Q value? Well, I go to the I go to Appendix C in the National Building Code, and like I said, you come down and like you don't see it here in the L's. That's because instead of having it here alphabetically, you go to the next page. Lévis is a suburb of Quebec City. So you come here, you see this is Lévis right here, and therefore that's where you will find that one. Some of you might have known that, and some of you might not have known that, but okay. So basically what we want to do is, and like I said, when I do this in real life, okay, guys, even though I do this constantly, I take one of these, I put it across the row, and I make sure I get the right value. So I don't act, well, here it doesn't make much of a difference. They're all about the same values because it's all Quebec City. But sometimes like you can make a mistake between 0.91 and 0.68, and it's very embarrassing when you take the wrong value, especially if it's under the value that you're supposed to be using, and you underestimate your pressures. So in this case here, we have for a probability of 1 in 50 years, we're looking at 0.53 kPa, and that's what I need for my value of Q. And oops. So now, after that, it's a question of calculating the exposure factor. And as I told you, the exposure factor increases as you get higher up into the atmosphere, and that makes sense because as you go higher up in the atmosphere, the wind speeds are higher, okay? And therefore, and then of course, there's two types of exposure factors. One if you're in an open terrain, one if you're in a rough terrain. If you're not sure, be conservative, always use the open terrain, and this way you're automatically going to cover yourself for the rough terrain. And now here I have a value of 6. Okay, so remember that this has to be greater than 0.9. So even if I have a 5-meter building, if you put it in here, you're going to get something less than 0.9. Therefore, you should just automatically be using 0.9 for the CE value from 0 to 6 meters. And then after that, what you want to do is you want to calculate the height. You want to calculate the height of this exposure factor for the roof. Now, guys, this is something you're allowed to do, okay? And it's up to you. Remember, you guys are doing your calculations. You guys are estimating what the loads are on your building, okay? And here, of course, what happens is that they say that you're allowed to take when you ever have a gabled roof. In other words, a gabled roof is one that has two slopes. You're allowed to use the mean height. In other words, the mean height between the gable here, okay? In other words, you can use this height here for the height of the roof because, okay? And if you ultimately want to be really conservative, well, just take this to be the height. It's up to you, but you're allowed to take the mean height of the gable. This little triangle is called a gable. And therefore, of course, all it requires a little bit of trigonometry. In other words, you have 6 meters plus 7.5 meters tan of 30 degrees because this was 30 degrees here. Okay, and of course, I take this length here, and then I take this length here, tan of 30 degrees, which would give me this height here, and then divide it by 2. I'm in the middle, and therefore I get 8.2. And then when I put this value into the formula, I end up getting 0.96. So that's, like I said, I will expect you to do that for the test, but remember that if you take a higher value of CE, it doesn't hurt you, it only helps you in real life. So now, so the best thing to do, as I said, okay, like draw yourself a little table, okay, draw yourself a little table, and in that table, basically what this is, okay, I put the surfaces here that correspond in the order that I will go get them off the figure. I think it's I7, I forgot the number, in the figure that they gave you to go get the the CPCG values. And then basically this is just the equation written out here, IS, Q, CE, CG. And of course, if I only have 6 meters, then I would only have one column. If I go from 6 to 8.2, I have 2 columns. And then if I have even another height, I will go to 3 columns. And then after that, I would end up with 3 columns here, okay? And then basically, I just write the surfaces here, 1, 1E, 2, 2E, the ones that correspond to the load case A. So therefore, I simply write down the 4 surfaces that I will be calculating the pressures on. Then, of course, the importance factor is the same all the way across. And then, of course, the Q is the same all the way across. The only difference is that it's only the walls that go up to 6 meters. So therefore, it's only these 2 surfaces will have the CE value of 0.6. And then it's only the roof that goes above 6 meters. And therefore, it's only these surfaces that will have a value of CE of 0.96. And of course, this I copy straight from that figure. Okay, and don't forget, guys, for the exams, make sure you have access to that figure because you're gonna have to go to it because you are gonna have one problem with regard to wind pressure. So make sure you have that, okay? As a matter of fact, make sure you have a copy of the dead loads, a copy of that, a copy of whatever you need to do your calculation for snow loads, and and then the last problem is what we're going to be covering today. That you won't need anything except. So basically, like I said, what I do in my calculator is I calculate these 3 values all together, okay? And then I store it in my calculator. I don't know if you guys know how to store the values in your calculator. I take these 3 values, store in my calculator, then I multiply by there, put it there. Then I recall this value, multiply by that, put it there. And then there, and then after that, I do these 3 values here, store that in my calculator, and then multiply it by this value, multiply by that value. So that's how you can, minimize the amount of time you need to do the calculation. At the same time, if you do this correctly, you won't accidentally do it again by mistake, redoing these 3 numbers. So you do these 3 numbers because it's going to be the same value for this one, this one, this one, and this one. And remember, very, very important, are the negative and the positive. So this is the way that they set up so that you know that when it's positive, it's blowing towards the surface, okay? In other words, positive means that it's creating a pressure, and then if it's negative, it's creating a suction, it is pulling away from the surface. And it's very important because, like when you're doing a roof and you have a lot of suction, you want to be able to tie it down and so on. So the directions are very important. Okay, so that gives you a chance, and I think most of you. Okay, I think if I went through your assignments. Now it's over a week, but I do go through it. Like I have a cursory look at all the assignments, and I think in general you guys did very well. Okay, and some of them like super neat. I appreciated the ones that did a super neat, and so on. So here's the values, and like I said, this is load case number 8. In other words, what they mean is that this is the ridge here, okay, of your building, and therefore it is generally perpendicular to that one. Then of course you have the other case where you have parallel to the ridge, and that's called case number B, okay? Now, I'm going to tell you right now, read the exam papers very carefully, because I might ask you only for one case on the exam because of time factor. So don't do both cases. Read the one that I ask you and make sure you give me the one that I ask you. And if you do both, you're just wasting your time. I will not give you any credit for the second one, and I will not give you any additional marks. I will just cross it off and say not required. Understand? I won't even. So read the questions carefully, okay? I'm saying it now, and I won't repeat it next week, but remember, I will maybe ask you for load case A, or I might ask you for load case B. Just do the ones I ask you. Don't do both, in the essence of time, okay? Now, once I did it for load case A, in this case, in real life, I'd have to do both anyways, but okay, in this case. Now, for B, what's nice about B is that the CE values are exactly the same. So therefore, I don't have to recalculate those. So therefore, I don't have to go back and, and therefore, the only thing I have to do now is my table becomes a little bit more elaborate, because instead of having only 4 surfaces, I have also the 2 end walls here, okay? And therefore, I do the same setup. And of course, what happens in this case is that, like I said, this all stays the same. Okay, so therefore I do this, I multiply it by this here, and therefore negative, negative, negative. And what I like about load case B is that they're mostly all negative, especially from 1 to 4, they're all negatives, okay? And then it's only for 5 and 6, like depending on how you're going to show the direction of your wind. On the windward side, it's positive, on the leeward side, it's negative. So therefore, if you check your answers here, this is okay. This is the values that I got. Okay, and guys, when I'm correcting your exam, if you decide don't go over 2 decimal places, pretty redundant. Okay, and if your answer is within what I call the right order of magnitude, I will not criticize you, because if you put here 5.55 instead of 5.54, well, that's correct. And if you put 5.3 instead of 5.54, I consider that to be correct. So don't worry about that. Just, 2 decimal places is ample for these calculations, okay? Don't bother bringing it to 3 decimal places. It'll also save you some time when you want to copy them on your diagram. So now that we've did this, so now that we've got all our forces, and of course, keep in mind, okay, so basically what we want to do is we want to show these on a diagram so that we can relate to them. And therefore, as far as the diagram goes, okay, so what I do is very quickly, I sketch myself a little cross section here, and I put the cross section of the building. And of course, I show the wind direction. So I could then number this as number 1, number 2, number 3, and number 4. And of course, all the positive values, I show them going towards the surface. This one's positive, so it's going towards the surface. This one's negative. You notice, if you put a negative sign on the exam, I will mark it wrong. I want to see the direction. I don't want to see the numerical value here. If you put the right direction and you put a negative value, I will consider that to be wrong. Like I said, because certain programs, if you show it a direction and then you put a negative value, it's going to reverse it on you. So it's either, you understand? So therefore, and I want you to be able to realize that when you see a negative value, well, it's no longer a pressure, it is a suction. The roof wants to lift off the building and not push down on the building. The same thing with this wall here. It wants to pull away from the building and not pull towards the building. So that's why I want to see the directions of the pressure, okay, of the load, I should say. Okay, so that's, of course, that's for, so in other words, this is for the walls 1, 2, 3, 4, and, at the, well, E, in other words, for the E, some people like to call it the end of the building, some people like to call it the edge of the building, it doesn't matter what you want to call it. It's the E values. And of course, the E values should have the same signs or the same directions as the ones, okay, the non-E's, that's number 1. And of course, they should be slightly higher, because the wind always has a greater effect along the edge or the ends of the building than it does in the middle of the wall, because of vortices. I don't want to get into, And therefore, you just do the same thing. You do your little sketch, you show your direction, make sure you show the right directions for the load. And then after that, put the numerical value. And guys, if like what you can do, okay, you don't have to put KPA on everything. If you put here all values are, if you write this in KPA, then you don't have to put them here. But if you don't put it here and you don't put it here, I will give you 0 for that. Okay, no units, no marks. Keep that in mind, okay? Because for me, a 64 means absolutely nothing, okay? And if I say a 64 kilonewtons per meter, as opposed to 64 kilonewtons per meter squared, there's a big difference. So that's why these things are very important, the units, okay? Keep that in mind. You can either write somewhere that all my values are in KPA and then just put the numbers, or you can repeat it on each load, okay? So keep that in mind, please. So that was for the winds generally perpendicular to the ridge. Now, for parallel to the ridge, well, everything, like I said, the four surfaces are always have a suction when it's parallel, so therefore all the directions should be away from the building. And on top of that, these are the numerical values. And of course, the ones for the 1E, 2E are going to be in the same direction, except they're going to be a little bit higher. And that's exactly what happens. They are in the same direction and they're slightly higher. And that's for the 1E, 2E, 3E, 4Es. And if you guys have exactly the same value that I have, well, great job. It's either that we're both right or we're both wrong, okay? And then after that, now that you've done it for the, then you do it for the end walls. And of course, the end walls here, you have to remember that you have a value that goes from 0 to 6 meters. In other words, it's a constant. And then when you get up to the height of the building, it goes up slightly higher. So therefore, now in the old days, guys, in the old days, I'm talking about in the old days, when it came to the CE value, we used to have steps. You understand? We used to have steps. We used to have from 0 to 6 meters, 0.9. From 6 to 12 meters, 1.0. From 12 to 20 meters, 1.1. From 20 meters to, I don't remember the other value, 1.2. So we should just have different values. Now they've come up with a formula. But if ever you do this and you want to, you don't bother analyzing this as a triangular load. Just if you're doing this, consider this to be a regular rectangular load, which is much easier to analyze, okay, and use a value of 4.8. That would be perfect, okay? Now, we show it here because what we're showing is that it increases, but when I would actually be using this load to do my analysis, I would not even bother with this little triangle. I would just make it uniform here. And of course, it's much easier to analyze with a uniform load. And unless I'm putting in a computer program where it's very easy to input this triangular load, otherwise I would just make it uniform, and that's what I would do to do my analysis. Who cares if I add a little bit more force on my building? As far as I'm concerned, a little bit more is always better than a little bit less, and ultimately I'm only going to be that much safer. So just, some people get so bogged up that they're, like we're trying to be practitioners. We're not trying to become academics or physicists. We are engineers or we're technicians. We want to be practical. We don't want to have to. And practical means if you're going to simplify yourself and you put yourself on the conservative side, you're doing the right thing. Okay. So that's for the end walls. In other words, of course, this is the direction of the wind, and therefore the only positive values for the end walls are the ones that are on the windward side. This is what we call the windward side, and this is called the leeward side. And of course, here it's all negative. And of course, the same thing would happen for the ends or the edges of the building. And therefore, except the values would be slightly higher. And that's what it is. So I hope you guys feel comfortable doing this. I mean, it's not that complicated. I mean, it's not complicated for me. I've been doing it for so many years, but I hope you guys, I think you guys do have the gist. Does everybody feel comfortable with this, or is there any questions? It's all good? Okay. So what we can do then is we can get out of here and we can start talking about today's lecture. Okay, stop sharing and let's go on to, sorry. Okay, now let me go. Okay, now for most of you, it's not for all of you, this should be, most of this lecture should be like almost a review from what you've done in physics, okay? And for those of you that maybe were struggling with this in physics, well, this will be a good chance for you to maybe brush up on your deficiencies. And for those of you that, the only thing that I'm going to show you here is something new that you'll be able to, use to do some analysis. But the very first part of this lecture should be more of a review, okay? And guys, I'm going to take it slow because I want you guys to really digest this, okay? Because if you can digest this, whenever you're going to get into any type of analysis or whatever, you'll have a clearer picture of what you're doing, okay? And therefore, it's only going to simplify your life, and it's going to give you more confidence on what you're doing. That's what I'm. So now we are going to start. Uh, okay, we are going to start with. So here you go. Now, beam analysis. Okay. Now, basically, people ask me, what's a beam? Well, here's a textbook definition of a beam, okay? A structural element is designed to support loads applied at various points along the member. That's a textbook definition of what a beam is. In other words, it is a structural element. In other words, it is carrying a load, okay? And it can be a distributed load, it can be a concentrated load, it can be a moment, whatever it is, it's carrying a load, okay? And therefore, if I want to design that beam to be able to support or resist those loads, I should be able to determine what are the forces that the beam will be subjected to so that I can make sure that the beam has the resistance to keep those forces from making the beam break or collapse, okay? Now, next year is where you'll learn how to actually design these beams in reinforced concrete, in wood, and steel. You'll learn how to actually design them, what size they have to be. In this course here, I just show you how you have to evaluate what is the amount of force that each beam has to be, resisting up to. And that's what analysis is all about. So now, of course, reactions as supports and connections. And I say connections because you'll see I'm going to have one beam called a combined beam where I'm going to be putting a pin connection, and you should be able to calculate the reactions at that pin connection. Now, 3 types of supports are recognized for beam supporting loads, okay? And this, like I said, this is a review, okay? And it's, okay? Now, the most basic one, okay, a roller, okay, now we call it a roller, and that's because we need some kind of a diagram to represent what are we restricting at that particular point where the beam is being supported or at its reaction area, okay? So you guys heard about a roller support is capable of resisting forces in only one specified line of action and capable of resisting that force in either direction. Now, the reason why I say this is that when let me just, okay, I know that people have seen this in the past, okay? Like what they see is they see this. In other words, they see this like here, and then this is the diagram or the diametric way of representing a roller, and then they see that the beam is sitting on top of the roller, and they look at this as being like a ball or something. So they figure, yeah, it will prevent the force from coming down, but this thing will also prevent the force from going up. So in other words, we are restricting, okay, the displacement of the element being supported in one direction, whether it's upwards or it's downwards. So just because this thing goes up, that means that the reaction is going to be down. When this thing wants to go down, the reaction is going to go up. So in other words, what we're saying is that there's always equal and opposite forces. So if the force is coming down, the reaction will be up. That's why they call it the reaction area. And if the force is going up, the reaction will be going down to keep it in equilibrium. Okay, so that's what we mean. Now, what we mean by it will only restrict it in one direction, that's because basically, here, I don't know if you guys can see my ruler. Everybody sees my ruler? Okay. What happens if I drop the ruler? Am I restricting anything? So what does that mean? What does that mean when I just dropped? Does anybody have any idea what I meant? Like, in other words, here's my ruler, and all of a sudden I let go. What does that mean?
There are no supports.
There are no reactions. You follow? In other words, there's nothing, there's no reactions. Okay, there's no support, so there's no reaction. Now, what happens if I do this? Now, what does it mean that the thing's not falling? What does that mean?
You have the support.
In other words, there's reactions, right? In other words, this thing wants to go down, and it doesn't go down because this thing reacts it from staying up there by going up. Everybody follows? Now, my finger here represents a roller, okay? So in other words, this thing wants to go down and the roller is letting it go up, okay? Now, the thing about a roller is that if this thing wants to expand or contract because of temperature changes, what's the roller going to allow it to do? What is the roller going to allow this thing to do to the beam?
To have horizontal movement.
To allow it to move horizontally. And therefore, if I allow it to move horizontally, is there going to be a reaction? If I do not restrict how the beam wants to displace, will I ever get a reaction? Yes or no? I'm talking about this finger here, okay? Is there ever going to be a reaction if I allow the beam to go back and forth? Okay? Just tell me yes or no.
Yes.
Okay. If I don't restrict it like this and it falls, is there a reaction? There's no reaction. So if I don't restrict it from moving back and forth, is there a reaction? There's no reaction. Okay. So what a roller means, okay, what a roller means, okay, is that, first of all, how many possible displacements can you get at a support? Does anybody know how many possible displacements you can have at a support? How many ways can a thing displace at a support? Do you believe that at a support, the thing can displace up and down? Do you believe that's one possible displacement? In other words, do you believe that this thing can go up and down? Do you believe that?
Yes, sir.
Okay, so in other words, at a support, you can have a displacement that goes up and down. So that's one direction. Do you believe that this thing can also go back and forth? So that's another direction. So that's two directions. What's the third direction that the member can undergo at a reaction area? Does anybody know what's the third possible displacement that the beam can have or a member can have at a reaction area?
The Z direction.
The which one?
I don't know. There is a X and Y and a Z.
Well, I mean, I can, don't think of it in terms of X and Y, just think of it up and down, side to side, okay? In other words, those are the two possible displacements, but there's a third one. What's the third one?
The side direction.
What? What's in the Z direction?
I don't know. I don't know how to explain in English.
Well, say it in Chinese, then we'll understand. How's that?
I don't know. Side to side.
Side to side. Side to side is this. It's either side to side is going to be in this direction, and if it's like this, side to side is in that direction. What's the third possible way that this thing can displace? Any suggestions from anybody?
Diagonally?
Diagonally? No. But I'm glad you're thinking. Look at my ruler. It's straight right now, right? Everybody sees that? If I put a load on my ruler here, what's going to happen to the ruler? It's going to do this. Everybody see that? And when it does this, what is that? What's happening here? How is it displacing here? It's a rotation. Everybody sees that? Like, in other words, it's rotating about that point. Okay. So the three possible displacements that you have is it can displace from side to side, it can displace from up and down, and it can also rotate. So in other words, if I have a beam, it can rotate about that reaction area or that support. And that's what we mean by a rotation. In other words, it's an angle here. Okay, so those are the three possible displacements that a member can undergo. Now, when I say I have a roller, all I'm doing is I'm preventing it from going up and down. That's a roller. Okay, so in other words, I only give it two ways of moving, and sometimes you'll hear this term, it has only 2 degrees of freedom. In other words, it can only go side to side or rotate. So that's 2 degrees of freedom. So that's a roller has one restriction, and therefore it still allows it for 2 degrees of freedom. It can either go back and forth or it can rotate. So that's a roller. And then so all we're saying is that when I put a roller, all I'm doing is I'm preventing it from going up and down in the direction of the roller. So if I have my roller against the wall this way, it still prevents it going up and down in that direction. So it's just the restriction of displacing in one direction. That's what a roller is. So, and what we do is that we tend to diagrammically convention for a roller. I don't know, you see this, they put like a ball or they put this little triangle with little wheels underneath. So here what they're trying to show you is that, well, this beam here, okay, when it's going to be loaded, okay, and all of a sudden, let's say I have this load. I have a load at an angle here, and of course that load at an angle there is going to create this like this. Well, at this point here, there's going to be no resistance. It's just going to move here, but it's not going to go up and down because I'm preventing it from going up and down. So therefore, I only have one reaction. In other words, I only have an R, whatever it is, one reaction. And that's how we represent a roller. When you guys are going to be driving over an overpass and you go over those expansion joints, well, those expansion joints, believe it or not, are rollers. They do not prevent the bridge from moving side to side. They only prevent the bridge from moving up and down. And that's what a roller is. So all those expansion joints that you see on a bridge are rollers. It has only one reaction. Okay. So that's a roller. Then after that, when you want to restrict it in two directions, okay, a pin support is capable of resisting forces in two specified lines of action. Okay, one is horizontal and the other one is vertical. So what we're saying is that if I decide to put a pin support, I'm not going to allow the member to move side to side. I'm not going to allow the member to move up and down. So since I'm preventing it from moving side to side, I have one reaction from side to side. Since I'm not allowing it to move up and down, I have one reaction up and down. So that's what what we do in terms of a diagram. We say, well, this cannot go up and down, and this cannot go from side to side. And because I am preventing two methods of displacing, then I will have two unknowns. I will have two reactions. And that's why when you guys were in physics, when you were doing this, you would put here an RY value, and here you would put an RX value, because those are the two possible reactions depending on the load that you might get where this thing is being supported. And that's how we represent it as a diagram. Okay, so that's a pin, in other words. And then the third type, of course, is where we restrict all the displacements. In other words, I will not allow it to go up and down. I will not allow it to go up and side to side. And I will, so in other words, if I have a fixed support like this, okay, if I try to fix this, when I put a load, look what happens. It does not rotate. In other words, it does not rotate about my fingers, and therefore I will have now a bending moment in order to prevent that rotation. So that's what we call a fixed support. So a fixed support is capable of resisting forces in two specified lines of action, one in the horizontal and resist the rotation of the beam. And how do we represent that diagrammatically? This is what we see. You draw a line and you just show this. So when I see this, all that tells me is that the beam cannot go from side to side, the beam cannot go up and down. And when the beam wants to bend, instead of like here, the beam can rotate like this, because I'm not preventing, but here the rotation will be straight and then it will start to rotate. And because I'm preventing from rotating, I will also have that reaction at that support. So here I have one reaction, two reactions, and three reactions. So I have three unknowns. Here I only have one reaction, two reactions. And when I have only a roller, that means I only have one reaction. So that's what it means. In other words, how am I preventing the displacement of the member where it's being supported? That's what you have to keep in mind. So if I'm only preventing it in one direction, I represent that as a roller. If I'm preventing it in two directions, I represent that as a pin. And if I also prevent it from rotating at the support, I represent that as a fixed support. So those are the three possible conditions that the support area can give the member. Or you can actually not give, that you will have to actually build to make sure that it corresponds to your analysis. Okay? Does anybody have any questions? Now's the time to ask if something's not clear. So far, so good? Okay. Now, so now that we have an idea of what these things are supposed to mean, and you know, like it just doesn't mean it's a ball or it's a little triangle or if it's a little hashing. It just means how am I restricting the displacement of the member where it's being supported. Okay. Now, when you're looking at beams, okay, sometimes you'll hear there's certain classifications of beams, okay, and of course the ones that you guys have been working constantly with in physics, okay, and the ones that you're going to see in most of your life is, okay, so beams are classified into several groups depending primarily on the kind of supports, okay, used. So the very first most common one is this, okay, when we say something is simply supported, okay, when we say something is simply supported, what that means is that we have a pin here and we have a roller there. So that means that here I will have one unknown, R, Y. Here I will have one unknown, Rx, because I represent this, I'm not allowing this thing from moving here. Therefore, if I happen to have a load in this direction, I'll have a reaction. And here all I'm preventing is the displacement in this direction, okay? So this is one beam has one unknown, two unknowns, three unknowns, and therefore this, you can use simple statics to do your analysis. So if there's not more than three unknowns at the reactions, you can always use simple statics. And that's what you guys learned in your physics, okay? So that's, now, you can also have, like for example, this would be considered simply supported, but all of a sudden you have overhangs. So these overhangs can still be analyzed as a simply supported beam, okay? And therefore you can also analyze all this beam with simple statics because you only have one unknown here, one unknown there, and one unknown there. And therefore I can still use simple statics, and I'll explain to you what we mean by simple statics to do the analysis of this beam. So that's a beam with overhang. And of course, here we have what we call a cantilever beam. In other words, it is being held at one end and there's nothing else supporting it. Now here, this cantilever, if you notice, okay, I represent it with this. In other words, it has to be fixed here. So what does that mean is that I'm preventing it from moving up and down. I'm preventing it from moving side to side. And also when this thing wants to rotate, you know, everybody can see that this beam wants to rotate from its original position. There's got to be something here to prevent the rotation, the reaction of that rotation, and therefore we have three unknowns. So at a fixed support, we're restricting all three possible displacements, and therefore we have three unknowns. At a pin, we're only just restricting it in two possible directions. We have two unknowns, and at a roller, we only have one unknown. And that's, you know, and that's because we're only restricting it in one direction. Restricting in one direction, one unknown, two directions, two unknown, three directions, three unknowns, and that becomes a fix. So all of these beams can be used simple statics, to solve, and that's what you've been doing in physics. You've been using simple statics to do the analysis of these beams. In other words, finding the shear forces, finding the bending moments, and so on and so on. So now that we have, then of course we get into a little bit more complicated. Then of course what happens here is that we have what we call fixed beams. Okay, so here all of a sudden, look what happens. I have one unknown here, one unknown here, and I have one unknown there. I have one unknown there. I have one unknown there. I have 6 unknowns, and I could never analyze this with simple statics to know the analysis of this beam. It would be impossible for me to use simple statics. 6 unknowns, can't do it. Okay. That means that this is a statically indeterminate beam. You'll hear that term sometimes in books. Okay. Now, here you have what we call a continuous beam. Okay, in other words, you have a support, a support, a support, a support, and the member is continuous. In other words, it is like one piece, like this could be one piece of steel, one piece of lumber, it can be one piece of concrete. It's, okay, now here what happens is I have, again, okay, if I look at this, I have one unknown here, I have one unknown there, I have one unknown here, one unknown there, one unknown there, and therefore if I add them up, I have 1, 2, 3, 4, 5 unknowns. This becomes statically indeterminate. I cannot use statics to solve my problem. I have to do and find another way of doing it. Okay, so that's also considered a statically indeterminate beam. And today what I'm going to show you, okay, is this here. How do we handle this here? Okay, so how do we handle a continuous beam? Okay, a continuous beam means that you have a roller here, you have a pin there, you have a roller there, and you have a pin that connects this part of the beam with this part of the beam. Okay, so this is called a combined beams. Okay, and guys, if you want to know where you see this a lot, next time when you're driving on the highway, okay, if you're ever driving on the highway, I can tell you right now. Okay, let me just if you're driving on the highway and you see a concrete overpass, and then, in other words, this is the support of the overpass, here's the support of the overpass, and you look at the concrete and all of a sudden you see this here, like this, and you see this here like this. I mean, it's going to be, I'm not drawing this to scale. And then all of a sudden you see the beams in between doing this, okay? Well, that is actually this, and this whole thing would be analyzed like a cantilever, and this would be and that's what this is. So these would be continuous beams, and it makes the analysis possible to use simple statics, and that's what these are. Okay, and if ever next time you walk into a Costco or a warehouse, if ever you look up on the ceiling and you look over a column, so in other words, you look up on the ceiling, you look at a column, you see the beam that goes over the column, it stops, and then there's another beam that gets attached to it here instead of being supported there. Well, that is that. That's a smooth pin, and it gets analyzed this way. Okay, so these are all real life situations where these continuous beams are actually built, and either at a roof structure or at an overpass. These things are actually, methods of, and then next year they should explain to you why we do this. Okay, so these are continuous beams, and like I said, today we will learn how to solve for this. Okay, it's not that complicated, but if you understand the concept of pins, rollers, and fix, it makes it much easier to understand what we're going to be doing today. Like I said, so if ever you hear a fixed beam, that means it's fixed on both sides. If it's fixed only on one side, it becomes a cantilever. And when it goes over more than one support, it becomes a continuous beam. And then, of course, you have a combined beam where you have a beam that's attached to the other beam with this, what we call a pin connection. Okay. Okay, so if there's no questions, I'm going to go on. And guys, feel free to ask me any questions on anything that you've seen in real life, and I'll try to relate it to what we're doing right now if it's related. If not, I'll explain it in another way. Okay, now I know that, so when a load is applied to a beam, this will, what happens? Okay, what happens when I apply a load to a beam? Okay, so in other words, I have a beam here, okay, and I apply a load. Okay, so what is this thing doing to this beam here? Does anybody have any idea what happens when I put a load on a beam?
It's pressure on the beam.
I mean, well, here it's not even a pressure. Here it's a concentrated load. It's a force. I put a force, so therefore this becomes a force on the beam. Yeah. So what happens now? I put a force on the beam. How does a beam react?
There's like a bending in the beam.
Oh, there's a bending in the beam. Good. And then also remember, all of a sudden I put a load, I'm going to have reactions here, right? In other words, this force is going to go partially here. This force is going to partially here. So I will get some reactions, okay? And then on top of that, I will have some shear forces, and I will have some bending moment forces, and so on and so on, okay? And I will explain to you so that you can relate to it, all that bending moment and the shear force that you did last year, what use is it, okay? So when you apply a force to what will, okay, it will cause reactions at the supports. So in other words, the first thing you do is I have a beam and I have reaction areas. The first thing I need to do is calculate the reactions at the supports, because once I calculate the reactions, I can go and calculate the other forces or internal forces that the beam might be subjected to. So I calculate reactions at the supports. And I think you guys, without realizing, that's what you were doing. Like, in other words, the teacher gave you a beam, he put all kinds of loads on it, and it says, calculate the reactions, calculate the shear, calculate the moments. And I don't know how well they explained that, but I will give you appreciation of what you're actually doing, okay? So reactions at the supports. And then the second thing is that you will have internal forces that will develop in order to keep everything in balance. Now, what are some of the internal forces that are created when you apply a load or a force on a beam? Does anybody know? Does anybody want to venture a guess?
Is it the actual force?
Yeah, but what kind of forces? In other words, what kind of internal forces may be created depending on the load? What kind of forces may be created by the external loads or forces that are being applied on the member, on the beam?
Tension,
Sorry?
compression,
Sorry?
tension force and compression force.
You can have tension force, you can have a compression force, okay? Okay, so basically, the internal forces on a beam that we constantly trying to evaluate, okay, is shear. And you guys did shear diagrams. This is an internal force. And you did moments, you did bending moments. That's an internal force. And then also, depending on how the load is applied, you can have axial forces. And that's what Jimmy's talking about. You can have tension or compression. Okay, so depending on how the force is being applied, so that's tension or compression. So that's an axial force. And then what's the last one? And you guys probably did this and you don't even realize you were doing it. Does anybody want to venture a guess what the last one is? Any guesses? Did you ever hear you guys talked about torsion in physics? Okay, so those are the 4 possible forces that can develop, all depending what the load is being applied and how it's being applied. Okay, now, so very rarely we talk about torsion. Mind you, I can show you many situations where torsion will exist. Very rarely we talk about axial forces. And the reason why we don't talk about these two, particularly when it comes to beam, we only talk about shear and moment, is because in most cases, the loads are perpendicular to the axis and will not cause, and will only cause shear and moment forces. So this means is that when I when I have a beam here, I'm drawing a cross section of a beam, okay? When I have a beam here, okay, you're assuming that here's my load. Oh, I should have, hold on a second. Okay, here's my load. Here's a load I'm putting on the beam, okay? Now, when I put that load on the beam, I should have moved this over, but sorry. Now, you're assuming that that load is being applied. I should have drawn a little bit more accurate. You're assuming that that load is being applied right where the center of gravity is of your member, okay? That's what you're assuming. In other words, this load is being applied right at that point. As soon as this load goes away from that, well, guess what happens? Then you start getting torsion. So if ever your load is not applied, if the direction of the load that you're applying does not coincide with the centroid of your member, you will start getting torsion. So torsion is twisting in the other direction, okay? And at the same time, if I have a beam here like this, okay, and all of a sudden my force is being applied at an angle, well, I have that vector and that vector. Well, this one will tend to push into the beam, and therefore I will have some axial forces. So when the load is perpendicular to the beam and the load coincides, so when the load is perpendicular to the beam and the load coincides with the center of your beam, the centroid of your beam, you only have shear moments. And when it doesn't, well, you can have some axial forces, you can have some torsional forces. And that's when you have to calculate those other forces depending on how the load is being applied. Now, in your case, in physics, you only worried about these two. In most cases, these are the two that we are primarily concerned with, but you can have some axial forces depending if it's not perpendicular, and you can have some torsional. Like the most typical torsional situation I can give you is that I have a beam here that's along the edge of a building, and all of a sudden I have members only loading on one side, okay? And this creates a lot of torsion in the beam. So that's a real life situation. But if I have the loads on both sides like this, well, that can be almost guarantee you that you have no torsion. That's where you can have torsional situations. So let's talk about now. When the loads are not perpendicular and do not coincide with the centroid of the beam, this will cause axial forces and torsional forces. And that's what I just finished explaining, okay? Now, so we are just going to look at maybe some axial force a moment, and we won't worry about torsion right now. But so now, reactions at supports, okay? So first thing you do is you have your beam, you see the loads that the beam has to carry. The first thing you worry about, how do I calculate the reactions at the supports? Well, okay, if the number of unknown reactions at the supports is not greater than 3, in other words, I don't have more than 3 unknown reactions, like I was telling you before, Rx, okay, then the beam is statically determinant, and the reactions can be determined by the 3 equations of equilibrium. This is what we talk about, statically determinant beam. Okay, so this is a term you're going to read in books. It says statically determinant. That means that I only have 3 reactions or 3 unknowns, and I can use my 3 equations of equilibrium. Now, what are the 3 equations of equilibrium? Does anybody remember? Does anybody remember the 3 equations of equilibrium? Come on, Kenneth, this is where physics comes back to haunt you. Yavor, give me some kind of a guess.
Isn't it the sum of the forces in y
Exactly, the sum of the forces. Okay, beautiful. Okay, so beautiful. Thank you, Yavor. What took you so long to just throw that answer out there? You understand? Don't be shy. There's no wrong answers when we're doing the class. Okay, so basically, the 3 equations of equilibrium is that the sum of the forces in the x direction. In other words, if everything sums up to 0, it will not move in this direction. If everything sums up to 0, and it won't move in this direction. And if I take moments about a point, and if everything comes out to 0, it won't rotate anymore. So those are the 3 equations. In other words, that is the most basic, okay? And guys, I can tell you that these 3 equations, okay, I use these all the time to justify if that $4,000 that I spent for the software to do my analysis, these three equations will tell me whether or not my money was well spent. Okay, and I'll show you how to do that when we use ADA. Okay, but I can tell you that these are very powerful equations, and they can tell me whether the $4,000 of a program that they're trying to sell me, if it's even worth spending the money, just based on these three equations. Okay, so now. So basically, if the number of known reactions at the supports are greater than 3, then the beam is statically indeterminate. Because you have more than 3 unknowns, you only have 3 equations to be able to solve it. You can't solve it by simple statics. You're going to have to find a way of manipulating it. Now, I'm going to teach you one way today by the combined beams. I'm going to show you other ways after in the following weeks using the principle of superposition. So I will give you other ways, and then ultimately when it becomes too statically indeterminate, I show you how to use ADA, and ADA solves all your problems. And that's what ADA is all about. It's an analysis program that will calculate all the reactions for you, all the forces that you need to be able to design your structure. And that's what we're going to be doing with ADA. And I'm going to do it to as many structures. Like I will do it for trusses, I'll be doing it for beams, I will be doing it for all kinds of possible structural configurations. Okay. So now, okay, now shear and moment diagrams, okay, so that you guys can appreciate what you're actually doing, okay. Now, these diagrams provide the values of internal forces caused by the external loads applied to a beam. Can somebody try to explain to me what this is saying in their own words? And guys, take a stab at it. Can anybody have an idea what we mean here? These diagrams provide the values of internal forces caused by the external loads applied to the beam. Are you guys at least trying to think about an answer, or? Okay, let me do something. Here's a beam. Okay. Oop, I should have drawn it the other way, but I'm going to try to okay, here's a beam, and of course I'm going to be very lazy. I put a load on the beam. Okay, I have a uniformly distributed load, right? And all of a sudden, and I know you guys like numerical values, but I don't care. This can be 10 meters. Okay, this can be 1 kilonewton per meter, and so on and so on. Okay, now, of course, first thing I do is I calculate the reactions. Okay, so in other words, I would probably calculate my reactions, and of course, if I calculate my reactions, I end up with 5 kilonewtons here and 5 kilonewtons there. Okay, those are my reactions. Fair enough? Does everybody agree with me? Okay, now, what I want to do is I want to cut the beam here. I'm cutting the beam there, and all I'm seeing is this part of the beam here, like this. So I cut the beam at 3 meters. Okay, I cut the beam at 3 meters. I have 5 kilonewtons here. That's my reaction. That stays the same. And then here I have 1 kilonewton per meter. We agree? Right? Is this in equilibrium? No, it's not in equilibrium. But why doesn't it move if it's not in equilibrium? In other words, I put my beam there, I load it, I cut part of it, and I look at that section of the beam, and it's not in equilibrium. If something's not in equilibrium, something has to move. Let me give you an example. Yavor, you're stronger than me, right? And if my feet can resist you pushing on me with 100-pound force, right? Okay. And if my feet cannot resist that 100-pound force, what's going to happen to me? In other words, I'm standing here. This is me. Okay. And this is you. And you push me and you put 100-pound force on me, and I cannot resist 100-pound force. What happens to me?
You're gonna get pushed back.
Exactly. That's what it means. Okay. So in other words, things are not in equilibrium. Now I look at this. I do the sum of f of y's. I do the sum of f of y's. I do, and I take upwards as a sign convention to be positive. I have 5 kilonewtons upwards. This is net going down, so I put negative 1 kilonewton per meter times 3 meters. Do I equal 0? What's 5 minus 3?
2.
Okay, so how come this beam's not moving if I still need to have 2 kilonewtons for it to stay in equilibrium? How come it's not moving if I need 2 kilonewtons of force to keep it in equilibrium? For this to be in equilibrium, I need 2 kilonewtons pushing up, right? Everybody agrees? So guess what this does? Guess what this force is here? This force here is 2 kilonewtons. Everybody agrees? And that's the internal shear force that has to develop, theoretically, that has to develop in order for this beam to be in equilibrium. So what the shear force diagram does, it tells you all the upwards or downward forces to keep everything in equilibrium. And that's the internal forces, okay? So that's what a shear diagram does, is that anywhere along this beam, when I want to know what's happening inside the beam, in other words, I have so much coming down, how much do I need to push up? And for example, if I went to this side of the beam, it would be the other way around. How much of it has to be pushing down in order, you understand? So these are the internal forces that keep everything in equilibrium anywhere along the beam. And that's what we call a shear diagram. So anywhere along that beam, if I want to know what's the internal force that keeps everything in equilibrium regarding the up and down direction, that's the shear diagram. So that's the shear diagram. Now, if I look at this, so that's what the shear diagram does. It gives me all these internal forces. Now, if I look at this, right, and if I take moments about any point on this beam, if I take moments about this point here, or if I take moments about this point here, and if I take moments about this point here, if the sum of those moments are not equal to 0, can everybody see that this beam wants to rotate this way? Everybody can see that? Or are they having problems seeing that the beam wants to kind of rotate around that point? Can everybody see that? Now, because it wants to rotate and it doesn't rotate, then there's going to be a rotation in the other direction to prevent it from doing it, and that's your bending moment. So your bending moment diagram is all the internal rotations that have to occur in order for this thing to stay in equilibrium. And that's where the bending moment in the shear diagrams are all about. So the thing wants to rotate this way. The bending moment on the internal is going to counteract that and keep it in equilibrium. This thing wants to go down. Therefore, the shear forces are going to counteract it to stay in equilibrium. And that's what the shear diagram does, is for all the vertical internal forces that can develop. And the bending moment is all for all those rotations that can develop in order for the thing to stay in equilibrium. I hope you have a better understanding of what these things are all about. So now, when it comes to sign convention, guys, these are sign conventions, okay? Remember, the reason why we have sign conventions so that when we put this on a diagram, if we're consistent with our sign convention, we will, algebraically come up with the right answers. That's all it is, okay? So the sign conventions for shear is this, okay? The shear at a section is positive. There's no such thing as positive or negative shear, guys. This is just for when you want to put the information on your diagram. But there's no positive shear, there's no negative shear. There's only shear. As a matter of fact, in nature, can somebody tell me how many forces there really are in nature? Does anybody know how many forces that we actually have in nature?
Is it 2 or 3?
It's 2, Emmanuel. You were
Okay,
right.
yeah.
Okay, there's
I
only
didn't
2.
know if friction was one too.
In other words, in nature, we only have a push or a pull. Everybody understands that? Nature either pushes or pulls. And all these other forces that we talk about are a combination of how those push and pulls work together or work against each other. Okay, and that's so a shear force, okay, there's no negative shear, there's no positive shear, okay, and when things get pushed together, it can either cause, you understand? So there you go. So now here, the shear is positive when the portion of the beam to the left ends up moving upwards with respect to the right. Okay, so if I look at my beam and if I say that this part of the beam is going to be moving up with respect to the other side, I consider that to be a positive shear. So on my shear diagram, I will put it on the positive axis, and if it tends to go down, I consider it to be a negative shear. I will put it below my axis, because what you're actually doing is that you have your axis where everything is 0. So do you want to know whether I should go up here and down here, okay? Now, this is for your shear diagram. Now, for your moment diagram, the bending moment is positive at a section when the top of the beam is in compression and the bottom of the beam is in tension. That's the only way you will define, and you guys should just read this 14 times or 5 times and keep this in mind, okay? When we talk about positive moments or negative moments, it's got nothing to do with your sign convention. Counterclockwise is positive, clockwise is negative. That's nothing. The sign convention for bending moment is that if the tension is at the bottom, we consider that to be a positive moment. When the tension is at the top, we consider it to be a negative moment. Okay, and that's just to tell us how the fibers are being affected by the way the beam is being bent. So positive moment means like, so in other words, here, the load here, okay, the load here is causing all the fibers here to be in tension. The tension is on this side, so we call that a positive moment. Here, the load is pushing upwards, okay, and all the tension is at the top here, and that the compression is there, and therefore we call this a negative moment. So we know when we say positive and we say negative, we just know, is it the underside that where the fibers are in tension, or is it at the top side where the fibers are in tension? That's what we mean by positive or negative moments. That's all we mean, okay? And it's nothing to do with counterclockwise is positive, clockwise is negative. That's sign convention. This is for moments, okay? So when you're looking at, for example, when I look at ADA and it gives me the results of an analysis and it shows me that it goes positive here, it goes negative there. Oh, all the tensions on this side of the beam, all the tension on that side of the beam, all the tension. And that's what that tells me. That's what I have to realize, nothing else, okay? And when it says shear, that means this side of the beam wants to move up with respect to that side of the beam and so on and so on, okay? So, and of course, if you keep this in mind, it's going to help you to draw your diagrams. That's what you have to keep in mind. Now, so now let's take all of this, and this is going to be, the first one is more like a review, okay? I'm going to review this. And of course, after that, we will do one with a combined beam, and that's going to be this what I want to introduce in structural analysis. So this is just a review. Now, here I purposely, okay, I purposely put a force at an angle so that we can end up getting, okay, some kind of a axial force in the beam, okay? So that's why I did that. So I just want you to realize that as soon as the beam is not 90 degrees, you will have an axial force. Okay, so in theory, what I need to do is I need to be able to analyze this beam. In other words, I have to be able to calculate what are going to be the reactions at the supports. Now here, if we go back to what I was saying, here I'm representing as a pin. That means I am restricting the displacement here in this direction. I will have an Ry value, and I'm restricting the displacement in the X direction. I have an Rx value. That's what this represents. I'm only restricting how it can displace. And here, all I'm doing is I'm not allowing it to move in this direction or that direction, whichever way, okay? And therefore, I have only an Ry unknown. So I have one unknown, two unknowns, three unknowns, three unknowns. That means I can use the sum of f of x, sum of f of y, and sum of the moments to be able to solve this. And I should be able to use those three equations of equilibrium to do my analysis. Now, so of course, this is this represents how your supports are going to, or how the supports are going to prevent the displacement of the beam at the supports. That means that if this was like so here I would have an expansion joint. It will allow it to go back and forth, but it wouldn't be able to make it go up and down. And here, of course, I would have to have a pin that doesn't allow it to move back and forth as well as up and down. So now, first thing I do, of course, is I represent this in a free body diagram. In other words, what I've done here is I've broken this into two, each one of its vectors. And of course, that you do by trig, so 30% here, and you do that by trig. And here is where my free body diagram, I say I have an Lx, an Ly left, and an Ry. So I have 1, 2, 3 unknowns. This comes down to 1,000 pounds acting downwards, and this is 1,732 pounds acting horizontally, okay? So now, from here, I start calculating my reaction. So the easiest one to calculate, of course, is I do the sum of f of x. Sum of f of x is equal to Lx. Now, I'm assuming Lx is in this direction, plus 1732. Do I have anything else in the x direction? No. So I have to say that all of this to be in equilibrium, they all have to add up to 0. Now, I end up getting a negative value here. What does that mean? What does it mean that I have a negative 1732?
It's in the wrong direction.
That's right. In other words, the direction that I assumed is incorrect. That's correct, okay? So in other words, the assumed, so you can assume any direction, and this will tell you if the direction you assumed is correct. So here, all of a sudden, my Lx is going this way, okay? So what this means is that from this point of the beam here to this point of the beam here, I will have an axial force. In other words, this will cause these fibers to go into tension this way. After that, here the axial force is going to be 0 because this is free to move. There's nothing to restrict it. So this is the only area of the beam that I will have axial forces because it's being prevented there and it's being acted upon there, okay? So that's where the axial forces go. Here, the axial force here, the tension is 0. The tension here is 0, and the only place I have some tension force is in this little section here. Isn't that amazing? Because why? Because here I don't restrict it. Here, there's nothing to restrict it, and therefore the only place I have tension is right there. Now, guys, I know how they teach you to do this in physics. Don't do what they taught you in physics. I'm going to show you the correct way to do your reactions. So therefore, you can double check yourself, because if your reactions are incorrect, your shear diagram is incorrect, your moment diagram is incorrect, your whole analysis is incorrect, okay? Now, I know that if I want to calculate Ry, I take moments about Ly, and then I can calculate the value of Ry. So in other words, like for example, now this is a sign convention, guys. Okay, now can you listen to me very carefully? When I do this in real life, okay, everybody agrees that we need a sign convention. The sign convention is to know what are the values I'm going to be putting in my equation based on what I decide here, okay? That's what the sign convention tells me. That's all. How do I treat it? Do I treat it as a positive or do I treat it as a negative? That's what this means, okay? Now, when you're writing these equations out, so in other words, where's my, okay. So in other words, I'm taking moments about this point here, okay? Now, why do I take moments about that point there? Because when this is an unknown, ry, and when I multiply it by a distance d equal to 0, it eliminates that unknown. That's why I take moments about that point, because what's a moment? A moment is a force times a perpendicular distance, and here the distance is 0, and it eliminates that unknown. So therefore, and then of course this one goes right through there, and that distance is 0. So therefore, I eliminate. Okay. So now, when I write these equations, I start with a sign convention. Now, I did this because you guys always have counterclockwise is positive. Okay, so let's take that. Let's start with that. I don't want to confuse you. Now, the first thing I do is I start from the very end of the beam and I work to where I'm taking moments about. So that's the first thing I worry about. Now, when I write my equation, the first thing I worry about is this is a moment. So therefore, it's got a constant value in my moment equation. Now, according to my sign convention, is this moment positive or negative? According to my sign convention, you tell me. Does anybody want to venture a guess? My sign convention is that I take counterclockwise as being positive. I consider that to be my sign convention. Is this moment turning clockwise or counterclockwise?
Clockwise.
Therefore, according to my sign convention, how do I write that in my equation?
Well, it's gonna be negative.
A negative. So that's the first thing I worry about, is always a sign. That's number one. Now here it's a constant, so therefore I just put the value. So that's very important. Now, look at this load here. Just look at this load here. First thing I worry about, with respect to this point here, will this load rotate this way, or will this load rotate the other way? Which way will it rotate? Will this load here, with respect to this point here, because I'm taking moments about r here, will this load want to rotate in this direction, or does it want to rotate in this direction? In other words, does it want to rotate clockwise or counterclockwise?
Counterclockwise.
Okay, so it wants to rotate counterclockwise. So what do I do in my equation?
It's going to be positive.
Put a positive side. So guys, before you worry about anything else, you worry about your sign convention. Okay, so now that I've got my right sign here in my equation, now I remember a moment is a force times a distance. So that's what a moment is. So therefore, what's the force? The force here is 800 pounds per foot. Well, that's not the force. That's the uniformly distributed load. And it's when it's multiplied by 4, that becomes the force. So here's my force. Then what's the distance? Well, you know that for a uniformly distributed load, it acts about a centroid, right? So therefore, it's this distance divided by 2 plus the distance away to where you're calculating your reaction. So therefore, it's 4 divided by 2 plus 4 and 8 and 12. Guys, if you take it, okay, so here's my force, here's my distance, okay? So don't look at it as being, don't change these into concentrated loads, leave them as distributed loads, and remember that where are they acting? They are acting about a centroid, okay? And like if, now, so that's, now, Ly, let me clear all this drawing. Okay, Ly, first thing I worry about. I'm taking moments about this point here. Is Ly rotating clockwise or counterclockwise? In other words, when this force wants to push up, it's as if I'm attaching a string here. Is this thing going to want to spin around that point this way, or is this thing going to want to spin around the point this way? In which direction does this thing want to spin?
Clockwise.
Clockwise. Therefore, according to my sign convention, what does that mean?
It's negative.
That's why, and that's why I put a negative. Okay, so I always worry about my sign convention. Then what's the value of the force? I don't know, Fy. So I put it as Fy. And what's the distance? Well, 4 plus 8 is 12 feet. So now, okay, now I move on. I look at the 1,000. Before I do anything, what do I worry about? When I look at it with respect to this point here, is it going clockwise or counterclockwise? Or does it want to rotate this way?
Counterclockwise.
And according to my sign convention, what is counterclockwise?
Positive.
And that's why I put a positive value there. Then I worry about the magnitude of the force, which is 1,000 pounds. And then I worry about the distance, which is 8 feet. So, and that's what gives me my moment. This part of the load here, okay, does it want to rotate this way or does it want to rotate the other way? Okay. So always, guys, when you're writing these equations of equilibrium, your first concern, and I'm going to repeat it again, is put the correct algebraic sign according to your sign convention, okay? And therefore here, I see that this thing wants to rotate counterclockwise. My sign convention is counterclockwise is positive, and therefore I will put a positive value. And then I worry about the force, which is 400 pounds times 8 feet. That's the force. And then I worry about the distance, which is 8 feet over 2. So I always worry about my sign, the force, and the distance. Now, you look at the very last load, this part here. How does it want to rotate with respect to this point here? In other words, when I look at just this load here on the beam, how does it want to rotate with respect to this, the point I'm taking moments?
Clockwise.
Clockwise. Therefore, first thing I worry about is putting a negative sign. And then after that, I worry about the force, which is 400 pounds per foot times 2 feet, and then the distance, which is acting at the centroid here, okay? And that's why you take a distance of 2 over 2 feet. And then once you, and then this, for this whole thing to be in equilibrium, it has to be equal to 0. And therefore, if you do, okay, so therefore I end up doing the math. And if I did it correctly, okay, I end up with 5,300 pounds. Now, in physics, what they show you is that, oh, I've got my Ly. Let me go get my Ry by calculating the sums of f of y's. Don't do that. That is absolutely wrong, okay? Because if you make a mistake here, what do you think you're going to do with the other reaction? This mistake is just going to get carried into your other equation. So do not do that, okay? What you do now to calculate Ry, I take moments about Ly. Okay? It might seem redundant, but trust me, you do these wrong, everything else is wrong. And in the exam, of course, you'll get 0 for the problem, but in real life, it becomes even more detrimental. So if you have a way of always verifying what you're doing in real life, you always do it, okay? So now, if I want to calculate, now I've got my Ly, which is 5,300 pounds. I do the same thing to calculate Ry. I take moments about Ly, okay? Now, I kept the same sign convention because you guys are so fixated on counterclockwise as being positive. I myself, I decide what would be easier for me, okay? So for example, if I am taking moments about, I decide whether I want to use clockwise or counterclockwise because I like to keep my reactions anyways. I won't confuse you, but you guys are fixated on this, and I think that's one of the big mistakes they do in physics. They always lead you to believe counterclockwise is positive. No, counterclockwise is a sign convention that you choose, and if it happens to rotate in that direction, you have to give it a positive value in your equation. That's all it means, nothing more. It's got nothing to do with what's positive or what's negative. It's how the tension develops in the beam that tells you whether it's a positive moment or a negative moment, not the sign convention. Now, I take moments about what? Ly. So now what I'm doing is I'm taking moments about this point here. So that's the first thing I look at. This is the point, okay? Now, again, according to my sign convention, okay, this is positive. This thing is rotating. This is counterclockwise is positive. This thing is rotating clockwise. Therefore, I put a negative value here in my equation. And then after that, I put the value of the moment. Of course, this is already a moment. It becomes a constant, and therefore, I put down the whole value. Now, Here, I look at this force here. Does this thing want to rotate this way? Or does it want to rotate that way? Well, if I look at it logically, if this is like, if there was nothing else here, this thing wants to rotate this way. It's rotating the same direction that I've assumed to be positive. Therefore, I'll put a positive value in my equation. And then after that, I will worry about the force, which is 800 pounds times 4 feet. So here's my force. And after that, I will worry about the distance. Of course, it acts about the centroid. And therefore, I take 4/2. Okay? So that completes this here. Then I move over here. And I just worry about my sign convention. Here's the point I'm taking moments about. I look at this and I see, oh, look, this thing is rotating in the other direction of what I assume to be positive. So the first thing I worry about is my sign. Therefore, this thing is rotating clockwise. I assume counterclockwise to be positive. I put a negative value. Then I worry about the magnitude of the force. It's 1,000 pounds. And then I worry about the distance, a force times the distance, and there's 4 feet. And now I've taken care of that. Now, when I look at this here, I can do two things, okay? I can look at this